H8 and stuff, because I have a lot of like firmwares that I'm trying to hack and they're not, Windows 2, and I'm like, oh my god, only have that tool would make my life so much easier. I'm going to talk today about disassembling and patching hardware, basically recognizing circuit board layout motifs and basic circuit modification techniques. The screen's a little bit dark, so I don't know how well the pictures are going to turn out, but if you pull down the slides, I guess they're online right now, you can also follow on there if any of the images don't come out too well. Hugo asked me to sort of make a talk about this for REcon, and it's a little bit hard to gauge the audience's level of familiarity with hardware. So if this is a little bit basic, I'll try and read the audience and move faster. If not, then I'll try and take more time. But basically, today I'm going to talk about essentially the hardware reverses toolkit. So just like you saw before, an excellent toolkit for reversing software, I'm going to get you familiar with the kinds of things I use, my version of these tools when I reverse engineer hardware. And that involves things like identifying the basic circuit primitives, translating into schematics, identifying circuit board motifs, so you're not spending all day long translating schematics, and some basic circuit patching techniques. And if time permitting and the weather is right, I'm going to try and patch a circuit right here on that screen over there, and hopefully I'll make a fool of myself. So, the hardware reverses toolkit. Actually, it's kind of nice that I just followed up a talk about a really good talk about software reversing. So, the basic cycle sort of involves something like sort of static analysis with a tool like IDA, or the other tools we're seeing like Time8. Some runtime analysis with something like SoftDice and LEDVG, and I've got a patcher to go ahead and apply your patches once you figure out what you want to change. HexEdit, HackMan, HexWorkshop. So, hardware cycle is very similar. For static analysis, you tend to use your eyeballs and a continuity tester. We are sort of stuck in the 1970s, I guess, or whatever, but there is no automated tool for extracting connectivity of circuit board yet. Although for integrated circuits, you do have some sophisticated tools for that, but that's outside the scope of this talk. For runtime analysis, you've got oscilloscopes and logic analyzers and probes and stuff like that, and those are a lot of fun. And for patching, you've got solder and wire, or you can build your own drop-in active hardware patching like mod chips and man-in-the-middle attacks, boards to install, say, between the memory and the memory slot or something like that. I'm going to pare down the talk a bit and sort of talk about specific subtopics that are more, aimed toward people who have less familiar with hardware. So I'm going to be looking at sort of a lot of the static analysis, the quote-unquote IDA equivalent, how to identify components on a motherboard or on a circuit board, how to extract the connectivity, how to draw schematics and the conventions for recording the circuit extracted results, and some sort of high-level motifs, kind of like the FERT signatures you might apply to like an M32 library to help you save time and effort. And I'll go through some basic patching techniques. So, how to solder, the theory and practice of it, basic techniques for desoldering as well as for tap soldering to circuit boards, so you can do some basic modifications yourself. So, now we're seeing time. These are kind of the basic circuit primitives that you may encounter. They're passive, active components and some miscellaneous important components. If it's not on this list, usually it's a very interesting component, and you want to pay some attention to it and figure out what it does. A lot of times you have to sort of I have seen some components I've never seen before. I'm very excited. I'm like, oh my god, what's this? And so you're looking at everything around and trying to deduce what it could possibly do. Those are often the most interesting ones, but of course, I can't give you the guide to all of them. But in the broad selection of components, there's passive components like resistors, diodes, inductors, capacitors, and there's active components, ones that have gain, transistors and ICs, and a few others. So I'm going to avoid using any equations to describe components. Instead of try to focus on the intuitive understanding of what a component does. And what I'm going to do is I'm going to refer to everything as what it does to the energy in the circuit, because the important thing is when you're reversing hardware, you want to sort of kind of be the electron, as you follow around the wires, and sort of by doing that you can get a feel for why they might have put the resistor there, right? You don't need to know exactly why, you want to know what are they trying to do with this, why would it be here? So a resistor is basically an element that's used to either remove energy from a circuit or introduce a controlled amount of energy. And what a resistor wants to do is wants to heat up, right? So the Ohm's law, energy removal rate, the power that's dissipated is equal to the current through resistor times the voltage dropped. This is simplest current voltage converters. And so the common applications in modern motherboards and stuff is to typically when you see them, they're used to dissipate the excess wavefront energy in a high-speed transmission line. So just like my sound waves are echoing off the wall and so forth, because the walls have a very high impedance and it reflects off, a resistor would actually be like putting foam padding on the wall, so the waves that are going through the copper wires actually hit its destination and don't bounce back. So that's typically what you see them for. They're also used for setting voltages on high impedance nodes, like pull-ups and pull-downs, strapping points. So if you look at things where they want to set the frequency or the voltage of a particular chip, sometimes they'll strap them with resistors. They're used for pull-ups and tri-state buses, like the I2C and PS2 pull-ups. And if you see analog circuits, they're typically used for setting gains or dividing voltages. The good news is there's relatively few varieties to really identify. Since I'm in Canada, I decided to be unfair to use an American penny. But since a lot of people, our American audience, appear to be unfair to use Canadian pennies, so I'm using the euro cent. It's about the size of an American penny. So on the lower left-hand corner is your quarter-watt 2-pole resistor, which I'm sure a lot of you have seen. And then to the right of it are sort of decreasing size resistors. There's 1206 surface mount and 0402. When you read those numbers, what they are, it's the first two digits of the number times 10 in mils, which are thousandths of an inch. So 1206 is 120 by 60 mil resistor. That's the footprint that they have. And they get even smaller. 0201s are basically the size of a speck of salt or something like that. They're very hard to see. 0402 is about the smallest you can hand solder. So also resistors can be in array form. In fact, most of these components can be in array form. So here you can see the black components here. That's actually 4 resistors in a row of a value of 82 ohms. Or they can be screen printed. So you can see down here what happened is this is on a memory device. They actually take a squeegee and they screen print carbon ink onto the memory circuit to save money. And these resistors here are in fact used to sort of dissipate the energy that's flowing down the copper wire to prevent them from sort of reflecting. So, capacitors are used to store energy in the form of voltage potential for a time-delayed release. So in other words, what a capacitor wants to do is it wants to keep a voltage at a constant level. If you charge it up, it'll try and keep the voltage at that charge, minus the leakage in the capacitor. So the amount of energy you can put in a capacitor is proportional to its capacitance times its voltage rating. And the common application you see is for like smoothing out power supply glitches. So if you have a circuit that's very active and it's going to draw a lot of power, make a lot of noise, if you put a capacitor across it, it'll try to keep the voltage constant. And so a lot of people send me emails saying, oh my God, I knocked off a capacitor from my motherboard, but it still seems to be working. Why is that? It's because you probably knocked off one of these smoothing out capacitors, and they're kind of paranoid placed around the board, very conservative placed. If you lose a couple, it usually doesn't hurt you too much. They're also used for voltage conversion, bootstrapping, charge pumping, switch regulation, coupling analog signals with different frequency operating points from hertz to gigahertz, and they participate in a lot of complex filter implementations. So there's a lot of varieties of capacitors out there. In fact, I'm kind of a capacitor connoisseur. I really like capacitors because it's like the medium of like materials and sort of science and all these different things. It's really kind of neat to understand all the properties of them. I won't bore you too much with my diatribe, or not really diatribe, sort of pontificating about capacitors, but kind of on the left-hand side are some kind of smaller through-hole ceramic capacitors. They're all rated microfarads. I kind of put the rating on them to get an idea of the relative amount of capacitance each one can have. So the ones on the left are relatively small. The ones on the right are relatively big. Even the right-hand side one is like, kind of looks like a big one. It's 0.00018 microfarads. So you have to read the number on them to sort of tell what they are. Typically, the number is printed. It's the first 2 digits is sort of the value times 10 to the raised to the last digit's exponent times 10 to the minus 12 in picofarads. So the radioelectrical is a huge one, 1200 microfarads. The SMT capacitors are much smaller, kind of zooming in here because they're too small to see relative to the other ones, are shown here. The top one is aluminum electrolytic, so it's kind of got a big, bulky appearance, and it actually holds a lot of charge, but it's what's called a low quality capacitor. So if you're actually expecting it to sort of react quickly, it doesn't react very well. So you don't use it all over the place. Typically when you see these are indicative of large power supplies and slow signals and that sort of thing. The ceramic capacitors, the 2 in the middle, are kind of like the hot rods of capacitors. They're very, very fast. They're very capable capacitors, very stable if you get the right dielectric. And typically if you see those, they indicate that there's some very fast, maybe interesting circuit going on. And the bottom one is called a tantalum capacitor. It uses a kind of a more expensive substrate. They have a good quality, they have high capacitors typically use some power supply decoupling, although they have a reputation for exploding in a wonderful, brilliant white flame if you hook them in backwards or you put too much current through them. So actually, a lot of Japanese equipment will not use tantalum capacitors because it's too embarrassing to have exploding capacitors in their electronics, and so they will avoid using them at all costs. So capacitors can also be in array form. So here you can see these capacitors here, the four kind of silver dots on the top and the bottom. That's 4 capacitors in one package. And this is used actually on the backside of an FPGA to decouple it. They typically do this to save space in the board. And you can tell this from the resistor array because the resistor array sort of looks like got a glossy black kind of look to it. And this one actually has that earthy sort of ceramic look to it. It actually looks like the material. So you can kind of tell it's a ceramic capacitor. Inductors, they're used to store energy in the form of a magnetic flux. So capacitors are storing sort of as voltage. This stores as a magnetic flux, a collapsing and expanding magnetic field. As the magnetic field moves in and out, it interacts with copper and causes electrons to move. And what inductors want to do is they want to maintain a constant current. So as electrons move through, it wants to keep them moving at the same rate. And the amount of energy storage is proportional to the number of coil lines you see multiplied by the magnetic core capability. So the actual material that's inside the wires plays a big component as to how much current you can sort of keep moving. If you couple the flux of 2 inductors, you get a transformer. So they can actually move, allows you to convert AC voltages between different levels. Typically, if you see these in a motherboard, they're being used as a counterbalance to a capacitor in a power conversion circuit, or they're used to block high-frequency noise for like FCC compliance, or they're used in a complex filter implementation. So inductors, there's a lot of varieties of them. They're a lot more kind of all over the place, but I gave you kind of a representative feel here. In the top right, there's a sort of an adjustable air core shielded inductor. If you see an inductor like that, typically you're looking at an RF circuit, like a TV tuner or something like that. And a lot of times they have a little screw that you can turn to sort of tune where the circuit is tuned into. To the lower left of it is what's called a ferrite bead. It looks a lot like a capacitor, except it's a little more gray and metallic in appearance. And so instead of a ceramic dielectric, actually they use a ferrite composition around the wire. And this is used to sort of provide a little bit of inductance to block high-speed signals from leaking out your circuit and infecting other computers with radiation and stuff like that. In the lower left-hand corner is an unshielded inductor. It's actually a transformer, but typically if you see coils of wire, you can bet that's an inductor. No matter what form it is, there's a lot of different things. If you see a coil of wire, it's an inductor of some kind. And to the right of that is a shielded ferrite core inductor. It's a little hard to see because the screen's a little dark, but that one, what it has a coil of wires on the inside, and they put a box around the outside to keep the flux from escaping, and that allows you to isolate the signal a little bit better. Diodes are used to restrict the flow of current in a single direction. So now we're entering the realm of sort of semiconductors. Diodes essentially want to make current flow in one direction. And even though they're a semiconductor device, I call them a passive device because you can't get gain out of the diode. You can't put a signal in and get a bigger signal out of the diode. So common applications, you see these in rectification of AC to DC. They're essential component of switching power converters. They are sometimes used for ESD protection externally from the chips. A lot of times used for circuit protection against putting the battery backwards or power supplies being put in backwards. And more rare, they're used to clamp overshoot and undershoot in circuit boards. So these are some pictures of diodes. They come big, they come small, they come in surface mount packages, you kind of get scale for it. The interesting one is kind of right in the middle above the penny. It's got 3 terminals on it. And as some of you may know, a diode usually has 2 terminals. So what they do in these cases, because they're so small, it's hard to mount them. They actually add a 3rd dummy leg, and what you do is you just look where the copper traces are going and know which one is hooked up, and then you can sort of figure out the circuit from there. And sometimes they actually put 2 diodes in there. They tie the anode and cathode together for array use. So you got to be a little careful when you're trying to reverse out the diodes and figure out what's going on there. Transistors are, the basic active circuit element. It's the foundation, the rock upon which we all sit. We've got trillions of transistors in a room in all of our computers and nets and so forth. I'm talking here specifically about the discrete devices, the ones that kind of sit on their own. Typically, a transistor can be thought of as a device that varies the conductance between 2 other terminals. So it's kind of an electronically controlled switch or an amplifier. There's a lot of varieties of transistors. It's not important for this talk to know what they are, but it's just important to identify them, sort of know why you might see them on a motherboard. So even though like your chip has a billion transistors in it, you still have discrete transistors on a motherboard. And when you see those, typically that's going to tip you off that you're looking at a switching power supply, or you're looking at something for power management, something that will turn off stuff to conserve your batteries, or turn on stuff to add more kind of computing power if you want. They're sometimes used for level shifting in power management circuits. If you're looking at cell phones, sometimes you use the amplifier for the output of a single discrete transistor. And usually you have to rely on the package type and board layout cues to sort of determine what the function of the device is. So here's there's a lot of variety of transistors, sort of pull a couple out of my bin and threw them up. In the lower left-hand corner is a power bipolar transistor. This is the kind you might find in an audio amplifier. In the top left-hand corner is a quad match transistor array. It looks just like an IC, and actually has a little integrated chip on it. But if you read the part number and look it up, if you see this, it means something kind of interesting is going on. The guy who designed it really wanted 4 match transistors that are discrete, and so you might, you want to wonder why they did that, because that's a little unusual. There's the power FET, the big device over there, and the small signal BJT, which you guys might have seen before in like your college kits, if you took an electronics class. And the interesting one is now I've got again another 3-terminal device that looks exactly like the diode that we saw before, right? So here comes a little bit of confusion. You have the exact same package, transistors and diodes. So a lot of times you have to sit there and kind of mull over, am I looking at a diode or a transistor, am I looking at its location in the circuit. So ICs come in even larger variety of packages and functions, and typically you have to deduce the part function from the part number. You can't just look at a device and say, oh, that's, this is an AND gate or something like that. It just doesn't come out at you. So, so the most important thing to learn about sort of reversing these is sort of how to read the part number. So typically a chip has the following information printed on it. It's got the manufacturer's name, sometimes just a logo or a picture. It has the actual part number itself, which is usually a line after the manufacturer's name. It has a date code, which is usually a 4-digit number followed by a couple of digits. And so you can, like the date code here is 9751. This chip was manufactured in 1997, the 51st week, right before Christmas. And so, actually, a lot of times I use date code to identify the age of the hardware. So you can say, generally I'm looking for technology in the 0.25 micron domain, so I can call my search space for what kind of stuff I'm looking at. So that's actually a really useful cue. And then on the right-hand side is a lot code. There's an internal tracking number. So if you actually came back with a field return to Dallas Semiconductor, they can say, oh, this wafer in early in September that was processed, eventually it was packaged chip in December. Oh yeah, we had a problem with that lot. Here's your money back or something, right? Fat chance of your money back. But, so if you want to look up a part number, I know there's a talk really about cuckoo on Google, but I'm an old-fashioned guy and I use Google. God, actually Google. Did Google just come out? Anyways, so if you just plug in the part number, like you saw here, DS2118, I took off the suffix to MB. You put in and you say right away. This is a Dallas Semiconductor Ultra 2 LED SC SCSI terminator, right? So you know exactly what that chip is. Great. Google works great for that. If Google isn't working well for you, you can go to findchips.com, which is my other favorite spot. And what it does is it searches through the inventory of chip sellers for that root suffix. And so here you can see it found a hit for findchips.com in digit key, the 2DS2118 MB Plus, and even gives you the price, $3.31. So if I want to know, I can go buy it. And, they'll ship it to me in a day and I can put it on the board. So, findchips.com is a pretty good place to go when Google fails you. Sometimes you see strange parts. So, like, if you look at a VGA memory part, they have kind of appended, shortened part numbers because there's not enough space to print the whole freaking part number. Part numbers are that long for memory chips these days. And also on these really small parts, like the little tiny diode part or transistor part I showed you earlier, there's not enough space to put more than four digits on the top of it, right? So if you're trying to look up like, let me see if you have the slide for that. So if you're trying to look up, for example, the memory, what you do is you look at the upper right hand corner, you see the M, that's from Micron, you recognize that logo. You go to Micron's website, and a lot of times they'll have the part number decoder. And so you read out the FPGA code Z9BSJ, you plug it into their decoder, and it gives you the full part number and data sheet for that part. For the very small pre-terminal, like diodes and transistors, you just got to do a lot of guesswork sometimes. So what you do is read off the part number here. It just says 306 and F. The actual part number is FDN306P. And it can take a little while to sort of resolve it back, and there'll be some ambiguity, but usually it calls your search space enough that you can eventually figure out what the part does by looking at its connectivity and so forth. In the worst case, you have to take the part off and put it in a tester and actually characterize it, but that's not going to happen. So here's some common IC packages. These are all chips of various forms. I kind of tried to pull out some of the more interesting ones. On the left-hand side is a VGA and a pin grid array. Across the top is a plastic leaded chip carrier, and then the traditional DIP package. A really interesting one that's become really popular lately. I don't know if you're going to lose a microphone now, but this guy over here, that guy. I don't have a laser pointer. Those guys actually have no leads on them whatsoever. So when you look at it on the board, you just see these little metal like divots coming off on the side. And those, you got to be a little careful when you're trying to reverse those, because you got to look at the manufacturer's. What's the laser point here? Thanks. I don't have to do the jump here. So for these here, you have to be a little careful because a lot of times they have this metal pad on the bottom and so forth. So you need to look up the data sheet to sort of see what's on the inside. It's just not apparent. It's not really apparent. This guy here, this little tiny guy here, is also a chip. This guy's a single logic gate right there. And this guy, of course, is a Xilinx FPGA with a huge number of logic gates. So on VGA packages, one thing to note about them. So here you can see this is the top view, that's the bottom view. This is what it looks like when the chip is sort of revealed. It actually has these little solder balls on the bottom of them. So when you look at the top, it just looks like this big metal square. And unfortunately, no, you can't see the connections on it. So when you're trying to reverse a VGA package, usually the solution is you buy a second version of the hardware, you pull the package off, and then you have to look at the circuit boards. You have to destroy one piece of hardware. Or if you have only one of them, you pay someone with an X-ray machine and take an X-ray of it, and you can sort of see the connectivity underneath. So, and actually, it's not too hard to find the X-ray machines. Actually, like in San Diego, there's probably like 20 guys with X-ray machines you get to pay to do it.
How do you remove VGAs usually?
Typically, if I want to pull off a VGA, I get a heat gun, and I just kind of point at it until you kind of see it. What happens is you heat it up, you see it kind of shift slightly as the solder and kind of lets go, and the thermal stresses activate it. At that point, you just take a pair of tweezers and you pull it off, and I take some solder grain and clean up the board. That's destructive. If you want to reball them, actually there's 10 guys in San Diego who you just give a VGA and they'll reball it for like $50 and put it right back on again. So.
Is the X-ray machine a normal X-ray or special?
It's like a normal. It's like the kind they use in like an airport, except it's got a little ability to print a film after you're done with it, and it can have a little more resolution. It can fit the focus depth and so forth. So they routinely use the X-rays to inspect these packages during manufacturing, because sometimes the solder will short underneath, and you have to take a look. And so the same guys who have those assembly lines will have the X-ray and just say, "Hey, dude, here's $20 when you put this on the line. They can take a picture for you." So. Here's some miscellaneous devices. Just some crystals. These are used for time bases for kind of computers and so forth. They have a very wide range of packages, so I kind of want to give you an idea of what to look for. These are the more modern oscillator type packages. These are older CAN style oscillators. These are the kind of just simple crystals that don't actually do anything of their own. They're simply a piece of cut quartz with terminals on them. If you see a crystal in this kind of package, you almost always can guess its value. It's around 32 kilohertz. It's the traditional watch crystal, so to speak. And most of them have a value printed on the case. Usually crystals are a little interesting because if you're trying to do clock glitching or kind of time hacking on a device, you want to look there first to see if you can't override. The crystals themselves actually have a very weak signal, so if you just put a function generator over it, you can directly override the crystal just by putting a signal right over that. You won't even have to remove it. Some other stuff that can be fun to look at, you see potentiometers or resettable fuses on the motherboard. It can be tips that there's adjustable components that you might want to look at, so on and so forth. So potentiometers, for those who don't know, they're variable resistors, so they have three terminals. They have basically the primary terminals and one in the middle, which is a tap where the intermediate voltage comes out. They're handy devices for tuning, calibrating, and trimming. So now you kind of know all the basic components, The next thing that you do after you identify is you want to draw a schematic of these components so you can keep track of where everything is. The schematics are just a logical representation of the physical entities, and they'll help facilitate sort of the extraction of the meaning of the circuit by looking at it. So I'm going to go over some of the basic conventions used in schematics. So if you're looking at one, if you want to draw one, you kind of know what's going on. On the top line here, I have a set of transistors. On the left-hand side are BJTs, and the right-hand side are MOSFETs. And basically whether NPN or PNP, you have to keep track of where the arrow goes for the polarity of the device. And you can figure out the mapping of the package type to this schematic symbol from the manufacturer's data sheet. So if you look at it, they'll have a little picture of the package and say, here's the base, here's the emitter, here's the collector. So you can just figure that out from there. This symbol for a battery. These are two types of symbols for capacitors. The one we have a little plus sign over here means a capacitor can only be put in one direction. Remember the tantalum that blows up a nice brilliant flash, put it backwards? You put a little plus sign here so you don't do that. Resistors, just like a little wiggly wire. This is an inductor. These two stripes here represent that it's got an iron core to it. If it's an air core, it's just a loop of wire. This is what a crystal looks like. It's kind of a very literal representation of a piece of quartz with two terminals on it. Diode, the current flows this way through a diode, the direction of the arrow pointing, it doesn't come back that way. Potentiometer is a resistor with a little arrow on it indicating, sort of where the tap is. There's a fuse. Actually looks like the old classic fuses that you used to see, like the big screw-in fuses that you had in the old houses. And these are two symbols for chips. This is an actually it's a comparator, L311H. And this is just, the classic chip symbol is just a square. Because, people kind of ran out of drawing symbols for these complex chips to draw a box. And what they do is they number each pin on the outside of the box and they give the pin's name on the inside. So this is a serial level EEPROM, and you have 3 address pins, a ground, a power, a write protect pin, and a clock and a data pin. So that's how they, it's pretty straightforward how you sort of pin them out. The important thing to sort of keep in mind when you're reading a schematic and looking at it is the reference designators. And also on the circuit board, they apply the reference designator as well. So if you're like looking at, for example, these ambiguous components, like is this a transistor or is it a diode? They'll have a little piece of text next to them, right? And it may say D100 or Q100. If it says D100, it's a diode. If it says Q100, it's a transistor. So you can use the reference designators to give you a cue as to how to reverse out the particular component as well. There's a long list of stuff. I'm not going to go through all of them, but basically you take the first letter, typically, of the component and make that the first part reference designator, and then you add a unique sequence number to it. That's the syntax of a reference designator. I don't know why transistors are called Q. B is probably because Q is taken from transformer. I don't know. Integrated circuits are U, I think, for the micro symbol back in the day. So there you go. Another important thing is that, and a lot of times people who are just starting out drawing schematics will have a tendency to try and draw literal wires between everything like it is on circuit board. The better way to do it is to use wire by name. So here's two of these serial EEPROM chips I was talking about. See, this one's called U101, U102. So I've serialized the two of these, so two distinct entities. And instead of looking up SCL as an actual explicit wire, I just named it SCL. And that means it's hooked up to this SCL over here. This named SCL hooks to SCL over there. All these named power supplies are connected together, and so on and so forth. So that really helps clarify the schematic as you're drawing it out. Typically, when you draw a schematic, you want to do a flow where you do a top to bottom, sort of left to right convention. So top to bottom, the voltages are decreasing. Left to right, the signal, the current's flowing from left to right. So that's sort of, quick summary of how to draw schematics. Now I'm going to get into actually reading the PCB itself. So if you take a circuit board and you look at it, it oftentimes looks something like this. You have sort of like bright green areas and dark green areas, some areas that look gold, and so on and so forth. So the bright green areas is where there's copper underneath. That's where there's conductor underneath that. Dark green areas, there's no feature. And there are areas that look bright and shiny are actually where the solder mask has been peeled back so you can solder to it. The areas, copper normally looks copper color. The reason why it looks green is you put this coating over it so you don't accidentally short things together as you put the board together. So if you look at the cross-section of PCB, an important thing to remember is that there's multiple layers in a PCB. So this is actually a GeForce 2 graphics card that I took to a belt sander and sort of sanded it back. And so this is a cross-section. Here is actually the BGA package itself, and these are the balls underneath. This here is the chip, the silicon chip, and you see the bond wire going down to the package, and there's a via right there. And this here is the heat starter with the heat sink. This mates to the circuit board, and this is the circuit board's mounted on. You can see here there's these pieces of buried copper on the inside. You must better remember that they can hide traces on the inside, so you got to look out for those when you try and trace out a motherboard. Sometimes, in fact, the vias don't always go all the way through either, and that can be tricky as well, especially in modern cell phone equipment. That doesn't happen. Another thing to look for is if you look at the side of a board and you see something like a bright white layer on the inside like this, so this is the edge of a circuit board, you can see it's kind of got that kind of brownish color that is typical of the circuit board, but then there's this bright white layer on the inside. A white layer always indicates a very high quality dielectric, and so you want to sort of pay attention to that. That means someone's doing something very high frequency on the inside that they're kind of burying from you. So that's a good cue for wanting to take it to the exit or something like that. When you're trying to extract connectivity, if you have exposed traces, it's pretty easy. You see this line here, well, they're connected, so that's done, right? The problem is when, of course, there's no, they're buried traces and so forth. So if you do that, typically you take, a multimeter like this one over here, and they have a continuity mode where you dial up the continuity mode, you touch leads together, and you get a little beep come out. And so what you do is you just kind of plant the one end of the road where you want to start tracing, and then you just kind of sweep back and forth on the motherboard to hit a beep. And actually, it sounds like sort of a kind of a lengthy process to trace out, but you can usually find in 10 seconds or so where the connection is going. You have a general idea where it's going, you're just kind of running across all the pins of the chip and so forth. Eventually, you just hear the beep, and you kind of binary search and you say, okay, it's pin 42 of U506, and you say, okay, noted, right? So that's one method for finding buried traces. There's more kind of drastic measures like the X-ray machine if you really can't find it. So even though extracting traces is useful, typically if I'm reversing a circuit board, I only pull out one or two traces at a time. The critical ones, I don't want to spend all day extracting traces. It's kind of like going through the actual binary of an executable and translating to assembly instructions and trying to trace it out like that. So what I usually do is I rely on heuristics to identify the trace function without the full connectivity of the traces. So what you do is you fall back on inviolable physical principles that constrain the flow of electricity to cull the possibility space. And you also count on designers being really lazy. So you say, why would they do this? Well, they didn't do that because it would be too much effort, right? And so you count them as being lazy when they design circuit boards. So for example, the first motif is power traces are usually thick and short. So I'm looking here, this here is an edge connector. I don't even have to go to standard, I don't even have to look twice. I know that these thick traces here, those are power traces. These thin ones, signal traces. Why? Because it's easy to just make all the signal traces the same size, and the guy actually has to apply effort to make thick traces, right? And you want power traces to be big and fat, so those are power traces. Same here. These filled regions here are power traces. You can see they're connected to vias. This guy's ground. I don't even have to pull a probe. I know this is the ground plane. That connection is ground. That connection is power. Done. Here on this capacitor, you see this plus sign here. That's power. That's ground. Done. Right. So I didn't have to trace it out. Another one is impedance-controlled signals, usually thick and long. So you see these thin traces here, and you got this trace here that's sort of waving around and so forth. It's a little thicker than the other ones. It's got an inline resistor. This is an interesting signal. It's typically either a clock or a high-speed data signal. Somehow it's critical. The guy spent time to draw this pattern. He wasn't doing this just because he was bored, right? He had to make it a very specific length, right? And that makes it an interesting signal to you. So you want to pay attention to that. Another one is, so this is the high-speed board with the white kind of sandwich in the middle. There's no, this is your ground thing at the top. You can see this pattern of stitched vias along here. And I drew this pink line. It turns out there is a very high-speed trace right along here going to these two connectors. And so you can actually look for the gap between these ground vias. You can know there's a trace underneath it because they're trying to build an impedance-controlled box for those traces. So I didn't have to peel the board back or even get to an X-ray machine. I know these pins are connected to this. I don't even have to pull out a meter or anything like that. So that's oftentimes a motif to look for. Another one is you want to look for missing signals. So here is a ground plane that someone had flooded, and at the last minute they removed the via because they didn't want you to pull up the signal. This here to be the test reset signal in the Xbox, the original Xbox, and they pull it out so you can use an in-circuit emulator. But you knew, because they didn't recompute the ground fill and there's a missing hole there, that they removed an interesting signal. So when you look for places that was missing, eventually, okay, that is the interesting signal. You go back to it, and what you do is you eventually mill away the board and you reveal it and then access it. So that's good. That's a good hint too. Another one is that you see pairs of traces. So you see these two traces here that are laid out very carefully together, like this. This indicates the traces are coupled. It's called differential signaling. It's a way to reduce noise. And so, you don't have to trace them all. You know this. And actually what it helps you do is it helps you reduce what signal standard it could be. In this case, it's USB. But there's only so many differential signal standards. You don't have to, read up every data sheet to find what it is. You just know from looking at it that it's a differential signal. Another one is that if you see here, you can see two buses already at the very high level. You can see that they kind of run separate routes. And these guys went through and put more zigzags on each of these lines here. Indicates they really want these to be length matched. So you know that here is a data bus and the critical timing, and you can count the number of signals, look at the connector type. This one turns out to be SCSI, so it's pretty easy to figure out what it is. But it calls attention to itself as being a critical signal. I can forget all the other signals on the board. Another thing to look for is test points. So here you can see there's these little silver dots here where they applied solder to the board. This is in contrast to the vias, which here are just copper looking, right? So here they actually bothered to put solder on each of these points here so that when the manufacturer was debugging the board, they can actually just draw test points around it. You can actually have a technician code them directly. Well, what's good for the engineer is good for the hacker. So, if they need to figure out what's going on, you need to figure out what's going on, so you pay attention to the test points that they leave around. So it's kind of like following the breadcrumb trail perhaps on the road. Another one is, again, looking for similar functions of things grouped together. This is a picture from the original Xbox. This is from a hypertransport bus that I used to hack the Xbox. And this one here was just a dead giveaway. You see all these masses of signals are all wild and crazy here, and open signals here, and then wow, there's a big bus just laid out right there for you. So you really calls attention to me to say, this is interesting. There must be something cool going on there. I want to sort of look at what's going on. So with time, those are kind of the basic motifs. With time, you eventually learn to associate certain other motifs. So like when you look at a chip, you see a package or a logo, okay, this is a general type of component. This is the SDRAM, it's a flash memory. Here's a power regulator, there's other support components. So here is an example of so here's a motherboard. Some of you may recognize it. It's a GP2X, which is a little video game system. And so you can look at this, you apply some of your motifs here and sort of what's going on. So here's a Samsung part. I know Samsung makes flash ROM. It's got to be flash, right? I see over here WM, that's Wilson. Okay, that's a codec, so that's audio. Those big capacitors there, those are the bypass caps that sort of isolate the headphone voltage from the internal codec. That's the oscillator for the codec that sets the frequency. This is the SD card connector. This guy over here says net chip on it, probably involved with the USB connection. I see an inductor here, and I see some other supplies here. This is the power supply switching regulator, local switching regulator, so on and so forth. You flip the board over, take a look at the other side, say, okay. I see some buses here. These are the memory buses. This is the memory bus right here, so if I have to tap something, this is one of the places to start looking. This is the core processor. It's in the middle of the world. Here's a 32 kHz crystal. Here is a Maxim part this year. This whole circuit here controls the LCD bias. That's the LCD connector. This guy here is the VCOM amplifier for the LCD. And then I didn't actually look at this ahead of time. I'm just telling you based upon having looked at enough of these, that's what they're doing, right? And eventually, if you look at enough boards, you just look at them and say, okay, yeah, I've got enough of the schematics in my head that if you told me, okay, we want to modify this because we got to work with a different LCD. I can tell you, well, okay, here are the signals for the LCD controller. Here are the signals you got to look at for the LCD bias, and then you can go with it from there. So that's sort of the art of sort of looking at boards and sort of static analysis. Now I'm going to look into sort of patching, basic patching of circuit boards. So some soldering principles. So the key principle of making good joints is that everything needs to get hot. The circuit board, the component, and the solder needs to get hot, and it's a little tricky to do this. And I'll kind of go into a little more later. Work surfaces need to be free of oxide. And a lot of people, say, geez, buddy, how do you solder these little components and stuff? Well, if you can master chopsticks, Think of single grains of rice. They're about the same size as a small resistor, right? So maybe that's why, Asian guys or something. I don't know, but ever since I was very young, I've been thinking of very small things with my hands. So, I tell people it's not that big of a deal. You just get a little practice and it's not too bad. So the important thing is getting it out. I'm going to skip to some pictures and kind of starting to run towards the end of my time. Here's a cross section of a soldering iron. So this is the tip of the soldering iron. There's a component. So there's one. This is hugely blown up. I'm looking minuscule at it. This is the pad, and this is the ground plane and the copper sheet, right? And this is like common soldering problem that a lot of people don't get when they're first soldering. They won't make this joint right in the first place. And the reason why is they put the tip down, and the heat comes in. And first of all, the heat only really gets into the system through these little points. It's through the conduction. The soldering iron doesn't work by just radiating heat. It actually has to physically touch the component to get heat into it, right? And what happens is that as the heat escapes from the component, this component is going to heat up quicker because it's kind of got a finite size. But this copper is a great conductor of heat, and the circuit board is sucking the heat out, right? So what happens when they add solder, the solder beads up on this component, and nothing touches the circuit board, and there's not actually a connection that's going on, right? So a lot of times what you do to increase the heat conduction, you add, before you even start soldering, put a little bead of solder on it, which actually creates a liquid meniscus around the whole joint, and that actually causes a much greater area for heat flow, distributes heat more evenly, and you get good solder joint out of it at the end. So I just want to really kind of drive this point in because I see a lot of people starting with soldering and they get really frustrated. Here is a pad on the circuit board. It's a pretty big pad. And you can see these little vias here. Those are all going to the ground plane. We need a huge sheet of copper, right? This soldering iron is not big enough to heat it up. In fact, I've got in the corner here, I'm trying to pull heat into it. And you can see that this whole region here kind of looks dull still. What happens when it actually heats up enough, you actually see the phase change happen. It goes from solid to liquid. You can actually see it propagate across. And there's no progress being made towards making that into a liquid surface you can solder to. So what I like to kind of show people when I'm teaching them how to solder is the concept of a melt pool. So here, actually, I've managed to coat the whole surface with solder. This actually is all solid solder. It's not liquid. It looks liquid, but it's not. And in fact, what I've done is I'm dragging the soldering iron in this direction here, and what you'll see is there's a dark region. And I knew that this projector might not be good enough, so I false colored it, played around with the contrast. You can see there's a region here that's black. What's happened is that the melt pool is perfectly smooth and mirror-like, and it looks black, it actually looks dark. Right? And that is the only region where you could put a component and have it connect. Anywhere else on here, the component may look like it's sticking because the solder is a little plastic, but it's actually not making a connection. So when you're soldering, you need to look for that point of liquidity and actually connect the component to it. So here's an image of a good and a bad connection. Here you can see the solder's formed a good bead on the pad, and here you can see the solder formed a bubble on the edge here and no contact to the pad whatsoever because it's not going to heat up the board enough, right? The other thing I have advice for people who want to solder is to use flux. Flux is a chemical that's used to clean the work surface. When you heat it, it attacks the surface. It removes the oxide, makes it a lot easier. It's like magic, right? So, if you're ever in doubt, just smear flux all over everything, and it makes your life a lot easier. For people who want to desolder, the cheapest, simplest, quickest method is to use a low melting point alloy, like a chip quick alloy. So here is a spool of, I don't know what the actual chemical composition is, but this stuff melts at like slightly below the boiling point of water, right? And you just kind of flow it all over around the edge of the chip, and as the chip heats up, it just kind of floats right off the pads. And then you can kind of clean it off with some solder braid and so forth. So it's very easy to remove chips with this technique. It's very cheap, standard soldering iron. So patching is the next essential skill for the hardware hacker. So I'm going to go over 4 basic techniques: lifting chip pins, scraping solder mats, cutting traces, and adding wires. So when you want to patch, here's a picture of lifting a pin. So here is a surface mount component. This is an 8-pin device. You can see they're soldered down. What you do is you take your soldering iron, you put it right at the edge of the pin here, and you wait for it to get hot. And you actually wait for the heat to propagate to the whole thing. You don't want to start lifting the pin too early because this guy's metal, and he's going to pull the heat out. And you're finding if you put it down too early, you put the metal thing in, it sinks all the heat out, and all of a sudden it's solid again. So you wait till it's really hot, you take a knife blade in, and just kind of pry up with it, rotate it back, up comes the pin, and you can go ahead and patch onto that. You got to make sure that when you're prying up, you're not using it like a crowbar like this, but you're actually using a rolling motion, so the pin is actually rolled up. If you use a crowbar motion, it actually just torques the pin around the package. So, if you want to solder onto a point, for example, here, the solder mats, of course, you can't solder onto. Really, I would just use this via to solder onto, but I had to take a picture of something. You got to remove this green stuff right here. So you just take a knife, scrape it back until you see bright copper. The really tricky part is that you can see here there's this sort of thin layer. It looks kind of coppery, but not. And a lot of times just people think that they've actually scraped off all of the solder mask, but actually they haven't. There's a very thin layer of polymer left that's bonded to the copper. You know, you got to scrape it until you see bright, shiny copper, and then you can solder to that. Another thing you got to do is tap soldering here is you just take a pair of tweezers, you heat up the workpiece, you shove in the resistor, put a wire on it. So this is a tack solder job. There's another example of a tack solder job here. Short to ground for recovery mode. Okay, put a resistor, find the ground pin, tack solder it on, you're done, right? And you've got recovery mode going on. When you want to cut a trace, so here's this is through a microscope. So this is the tip of an X-Acto razor blade. And what you do is you take the knife and you sort of slide it up to the edge of the trace. The trace is actually slightly above the level of the circuit board. When you slide up the trace, you'll feel a dig. You kind of feel a catch, right? Once you feel the dig, you go ahead and you keep on pushing on it until it goes past, and then you roll the blade back. And actually what's happening here, if you can see it, is the trace is delaminated from the circuit board. It's made a good cut, good clean cut, delaminated off the circuit board. And actually I messed up. I slipped. So here you roll the trace back, and the reason why you want to roll the trace back is if you don't roll it back, the trace will actually have a tendency to sort of self-heal and fall back into place, so you haven't actually made the cut. So you actually want to roll the trace back and see the trace up. And here is, kind of a shitty view. Best I could get of the zoom in, you can see the trace is rolled up, and you can see actually the edge of the trace there, and the remaining trace is actually nothing but phenolic circuit board between the two. So that's sort of making a trace cut. So, I started a little late, and I will try to basically go into a really quick demo. Maybe I'll only make a couple connections of it, but I'll kind of show you a little bit about kind of a practical use. So, here's a problem statement of something, an actual problem I had to solve. Embedded devices often have an internal serial debug port that's connected directly to a processor, right? The processors today aren't like processors back, a bazillion years ago when we designed RS-232. RS-232 was made like in the 60s or something like that, and it uses like plus minus 7 volts to do signaling, which is not compatible with your processor. You plug an RS-232 point in your processor, you'll burn it out, right? So a lot of computers don't even have an RS-232 port on it. This one here, my laptop, does not have an RS-232 port. So really what you want to do is you want to convert this serial line to USB, but you don't want to have to build a custom dongle for it, right? So what you do is you go down to Fry's and you buy, or wherever your favorite place is, and you buy a little USB dongle like this one. Here's a keyspan dongle, right? And actually it's kind of almost made for hacking. You can see it here. On a light, but if you squeeze it, it just comes right apart. There's not even screws in it, right? And there's the dongle right here. Here's a picture of it up on the main projector over here. Now you're looking at a device you can take USB and translate to the old standard RS-232. Now remember, you didn't want to plug that directly into your embedded microprocessor because you break it. So what you're looking for is some internal signal inside of here that actually is at the right voltage level. So the first thing you do is you look at your key parts. These look interesting, right? And the contrast ratio, of course, is really bad on the screen. But this one here is a TUSB 3410, and this is ZT 3243. So you go Google TUSB 3410. Oh my God, RS-232 Ertis USB converter. Oh my God, that's the core converter. You're great, right? You pull on a data sheet, you read it. Life is good. This is a pinout from the data sheet itself, and so you look at these pins here, that's a serial in, that's a serial pin. So now I know what pins, I want to go ahead and solder on to tap them off and go to my embedded controller. We got to do a little more work though. So we push in the ZT3243 part number, and we get New York Dolls t-shirts at Burning Airliners, and we have 2 hits. That's not good. Right? So now we have to apply a little bit of guesswork. So we take the base number, 3243, and I know it's going to do something with RS-232, plug into Google, right? And oh, okay, you see here 3243DS. 3243 is a RH232 performance with a single 3.3 volt supply, blah, blah, blah. This is probably it. And what you realize after a while seeing this is that a lot of Asian manufacturers, cheap chip manufacturers, actually take these American chips, open them up, reverse engineer them, and put their own like prefix like ZT, some cheap Asian knockoff, right? And they label them, they cross-reference the American parts so the American designers recognize them. Oh, 3243, I used that for Maxim before. You know, I can buy this cheap Chinese part and plug it in. The truth is actually they're really bad parts. So you know, if you want your circuit to work, don't do them. Anyways, the other thing you can do to sort of make sure that these work. So here's the Max 3243 pinout, and these are ZT 3243 clone. You kind of take a look at it and say, okay, where are the thick pins? Okay, there's a thick trace coming out here. Third pin from the top right, oh, that's VCC. Oh, I see a V coming here to ground. Okay, this is probably a match. You're kind of happy, you get a good feel that we're not in the wrong ballpark, same number of pins. So you say, okay, these are the same chips, go on for it. So typically, you look at the data sheets to find those stuff, example, product overview, pin function. I won't go into details of an extra short time. But the basic idea now is that we've got enough of a schematic to get working. We've got a TUSB 3410. We've got the level converter that goes from the low-level voltage to the high-level voltage for RS-232 in the connector. I've identified pins 17 and 19 of the TSB 3410 as interesting signals. What I want to do is I'm going to cut this signal, because really when the processor is driving, you don't want the ZT3243 also driving the same. That's a conflict, right? But of course, when the process is sending, you can load it twice. It's not a big deal. So we've got to find one trace, cut it, and solder 2 wires to make this thing happen. So here, we want to trace the SIN, the serial in, so you've got a VIA coming down here. And if I had time, I was going to go through the details and sort of, take you more through it, but I've kind of already done that. So go to the live demo over here if I can, and hopefully I have enough time keeping you guys for dinner and stuff. On the back side here, let me zoom in a bit. All right. Focus. All right. So here on the back side, I'm trying to get a little contrast on here. You can see there's this trace going on right here, and I'm going to go ahead and cut that trace so you can do it without blocking the light to it so you can see what's going on. So I'm going to feel the dig, put it in, and then I'm going to peel that trace right back. All right, so I'm taking here, it's a scalpel blade. I couldn't really get my favorite knife through customs. I didn't even want to bring a box cut on there or anything like that. That would be really classy. So it looks like I managed to disconnect. I can see bright copper and so forth. So I've cut that trace. So that trace is now cut. Now I really want to solder on some signals to this microcontroller over here. And so I've got my soldering iron, I've got my wire, I've got my solder. Give me 1 second here. And I'm covering with the shadow so you can't see anything. All right, so what I need to do is I'm going to take a piece of wire here, and I'm going to cut off just a little piece. That I'm going to eventually tack that around this thing, off the length so I can actually hook up with something else. Alright, so when you're tack soldering, see now I've sort of jigged it up. It's not even like, I've kind of bent it to the right size, so it's almost the right place right there. I'm actually using the board itself to try and hold it in place, because I don't want to have to hold it in place really while I'm doing the work. So that's one thing to sort of help you out while you're doing it. And what I'm going to do is I'm going to take this wire to pin 19, which is one of the signals of interest that we identified, right? Light it up, take my soldering iron, and the first thing I'm going to do is use flux. Now, the interesting thing is that it's very cold in this room, so the flux is a little bit gooey. It's not going to flow, so I actually put a little bit on my tweezer here. I'm going to warm it up with the soldering iron, just hold it close to it. And what will happen is the flux will start running and sort of just coat everything with a nice gooey layer. There we go. So now I've got a little bead of flux hanging out right over there. Now I'm going to take this wire here, and I'm going to put a bead of solder on the end. And that's going to be the bead of solder that's going to be heated up and it's going to make to the pin. So I'm just going to go ahead and take this and sort of add a bead of solder to it. Okay. So now I've got a little bead of solder right in the end. And let me see if I can do this without blocking the light and still getting my head close enough to see what I'm doing. Alright, so take the tweezers, hold up to the side, apply a little heat to the workpiece, and I see the phase change happen, and I've got one wire attached, good and solid. Hooray. So I'll try the other wire really quick. One more wire. So I'm just cutting that about the same way. Cut off the other end for that. Go ahead and add a bead of solder to this one here. Can you guys see this at all?
Yeah.
Alright. And so now this one's going to be a little more challenging because I'm now trying to solder a pin that's between two pins. And one thing I forgot to bring was my desoldering braid. So if I screw it up, well, I'm not going to screw it up. Alright, here we go. I'm locating, very solidly locating the signal where it needs to be. I'm going to touch the wire first to melt the solder because I want to get that good melt pool going. And it's going to flow right up in the pin, wick right up. And there we go. That one is now attached to pin 17. Right there. So I've got that guy connected. Next thing you want to do is you want to hook a little ground wire into here. I could do a number of things. I can go ahead and get straight back to solder mask, do whatever. Actually, I'm just going to cheat. I'm going to hook onto one of the existing ground pins. These are lacking time. So what I'm going to do is I'm going to use these grounding gears on the RS-232 connector. These guys right here are typically hooked to the board grounding. Actually, if you can look close enough, you can see it. So what I'm doing, this is a big piece of metal. I'm actually pre-soldering. I'm adding solder ahead of time to increase the contact area between the soldering iron and the workpiece until I can see the phase change happen in the solder itself. I'm having a little trouble pulling it down because of a funny angle. But eventually, there you go. The whole thing just melted and the soldering iron sort of sank into it. There you go. Okay, now where's the metal? So go ahead and operate the melt pool. So now you can see it's soldered on because, you know, I pull it and work with it. So that's a good job. And there you go. So now I've attached the transmit and receive line and the ground wire. So if you were to plug this in, you can then go ahead and communicate with your embedded processor through this particular device here. So that's kind of a practical demo of how to use it. So you can see it's actually, it doesn't take, you know, a huge amount of time to do this. When you're finished with it, I did this, I probably did it a little earlier. You typically want to use a little hot glue or a little super glue, something to pack these wires down, because as you jiggle them around, eventually they'll come off. So you kind of just tack these wires down. And you know, if you want, you can go ahead and mill out a little hole in the case and have, you know, Ken actually did this for me because I just left it like this thing open. He's like, you gotta make it look good. So he did that for me. So. And so that's kind of, I guess, the basics of sort of looking up hardware, reversing it, and patching it. So, any questions? Yep, back there.
Yeah, when you do continuity testing, the signal that the loop sensor that you use is probably completely different from voltage and frequency and everything that the signal actually meant to go over there.
Yes.
Does that cause any problems? And in particular, I'm thinking, are there any anti-RE features that almost works or divert the signal that's different?
Well, typically, when you're doing the signal testing, you do it with the circuit powered down, right? So there's no dangerous voltages going on, nothing's going on, and what the signal testers do is they put a very, very tiny current through, one that couldn't possibly damage a circuit, and then they just look for the current flowing, right? So actually, when you do the testing, there's almost no interaction at all with the components, and it just extracts the connectivity of the circuit board itself.
I'm thinking like a redundant path that would be which give a false reading in the continuity test.
Oh, okay, yeah, that's a good question. So yeah, so if I had like a bunch of low value resistors hanging out to the side, you can get like a redundant path. Typically what these things do is they actually give you a number on the screen that tells you how good of a connection it is, right? So sometimes it'll beep, and you listen to it, and you read it, and it says 20 ohms. And you say, because its threshold is like, say, 100 ohms, right? You say, well, that's probably a resistor. You're looking for 0 ohms, and you just keep on beeping around until you see the 0 on the screen, or 0.1, whatever it is. So yeah, it's a good question, but yeah, sometimes you do find false positives. So, over there in the yellow shirt?
How do you find serial detect ports on a chip? You know, some basic.
Well, typically, so for example, like serial and JTAG ports, there's maybe some pictures here we can look at. This GP32X, I think, has one on it somewhere. Pretty sure it does. If you're looking at the processor, typically you can stare at it and you can guess a couple of things going on. JTAG is 5 pins, and usually they'll have a bunch of test points coming out, and it typically has a group of resistors hanging out the side, kind of like that. So there's 1, 2, 3, 4, 5. Yeah, I wouldn't lay money on it, just kind of quickly looking at it, but that's a good candidate because JTAG has 5 pins and usually has the terminator resistor that comes to the edge of the board. And so what you can do is when you turn it on, you can kind of probe it while it's during the power transit, you can see the clock happen and it'll go away, it'll go quiet. And you can start strapping, the thing will freeze and reset and start talking to your JTAG protocol, right? So you can sort of do that with high impedance resistors and sort of eventually discover the port. If you don't have the manufacturer data sheet. So, back there.
How do you recommend we go about on the order? We want to try and experiment it ourselves? How do you recommend we do that?
Usually, I think the best way is to just take a lot of stuff apart, you know, and look at it. You know, back in the day, like when I was first getting into it, my first computer was an Apple II, and that thing came with full schematics and source code. Right, so that was a really good time for learning stuff because you actually take the chips out and so forth. So if you want to get into more, a good place is to go to classic hardware, retro hardware, where you can find the schematics and so forth and learn the motifs for these devices. Next one.
Have you ever seen a manufacturer etch the numbers labels off the chips?
Oh yeah.
To make it harder for the engineer?
Yeah, I think they do that all the time when they're paranoid.
In this case,
Sorry?
what do you do when that happens to find out when the chip actually?
Well, a lot of times when they do that, they think they have some secret sauce. And so one thing they'll do, which is a mistake, is they'll etch only the part that they don't want you to find out. Right? So there's one part with something etched off, like, okay, this has got to be the memory and it's got to be the processor, right? So you okay, I'm going to start attacking that first, right? And then the next thing you do is you look at the package, and a lot of times when you're looking at it, you can classify, like a lot of times, and almost always, when they scratch off the top, it's a Xilinx CPLD, or it's a PIC microcontroller, right? Because they think, because those guys think they're badass, and they got something cool inside the PIC. And then, there's only so many footprints of PICs, and you'll see the ceramic resonator for the PIC and so forth. You say, okay, this guy's got a PIC, it's probably this series here, and then you can go ahead and hook up the pins to sort of pull out, where you think they might be to pull out the serial code, whatever it is, right? So typically, you can look at other cues on the board to figure out what's going on. In the worst case, you take the chip off, send it to Memphis, give them $100, and it comes back with no silicon on it, and you just read the manufacturer's labels right off on the silicon, you know what it is. So you can wait.
Yeah, my question goes along similar lines. Like, this board is not really particularly laid out to confuse you as a reverse engineer. In encryption, you have a strong diffusion factor.
Yeah.
Do you find that board manufacturers, I mean, how often have you found a board that is deliberately constructed in order to thwart your attempts by having all sorts of redundant traces and stuff that is high entropy?
I had a roommate in college who told me that if he ever became a board engineer, he would do that just to frustrate me. But he never became a board engineer. So actually, I've never seen a circuit board with redundant traces or anything to confuse me because the price of diffusing a electrical signal is you actually sap the energy out of the signal itself. You introduce reflections, and it's hard enough to get the hardware working as it is. So these designers oftentimes won't take that risk to do it. Now that being said, on chips it's a different problem because they have so much wiring resources and so much routing. There's actually people who write compilers for Verilog that will compile it to a set of gates that are redundant, have multiple paths, multiple switching paths to defeat things like power analysis. And those are really frustrating for reverse engineer. So yeah, it's done on the chip level, but I've never seen it at the board level. Back there?
Do you know if there are any sites or forums where people usually post like PCB layouts or data sheets that are hard to find, anything or something like that? Or
There are a lot of nice little sites I don't have, like, usually what it is, it's like a project site, so this guy, I've seen some guys do these like MIDI decks, where they build their own MIDI stuff, and they have like everything there, like the whole thing's open source, right? It's really cool. There is, for FPGAs, it's open cores, right? But I don't really know of any really repository. The blog that I have every month, I take apart a PCB or something like that, and I challenge people to identify it and figure out what's going on, or a circuit or something like that. But you know, that's by no means comprehensive. So, any other questions?
Can you recommend any sort of logic analyzers or like gauge static tables, or what would be like a good toolkit to get like if you're going to tap for?
So usually, if and it turns out, and here's actually an interesting thing for people who want to get into it. For your basic tools, go really cheap. Like your oscilloscope, just get like a 100 megahertz thing for day-to-day use. It costs like $300 to use or something. And when you actually find a board that needs something better, rent it. So you can get these, you know, $100,000 logic analyzers for like $500 a month or $1,000 a month, or you can get it by the week. And really, you only need it for that short period of time you're looking at it. And throughout the year, you only use it for like a couple weeks. You know, even I am a heavy user, I only use it every now and then. So typically, when I encounter a board that's too hard, I call Test Equity or Rentelco or something like that. And within like 3 days, I've got like this amazing logic analyzer on my doorstep and exactly what I want. That way, I'm not investing lots of money in these big pieces of static equipment that I never use. But you know, for brands like Tektronix, for oscilloscopes, the DPOs, those I swear by them. And for logic analyzers, I like the Tech ones too. They're getting pretty good. So.
What about like scanning electron microscopes and stuff?
So I have a Vickers scanning electron microscope at home. It's an old 1980 model that I'm still bringing up. It's kind of like an old car, like you buy old cars and you sort of refurbish them. So I'm in the process of sort of like redoing the circuit boards and stuff. It came with full schematics, it's great, right? A service manual. But a lot of times if I need an SEM, I actually go to the local university and I just find a guy, make friends with them. And you can usually get time in the evenings, because a lot of times grad students rent out time and I use it all. And you know, they'll show you how to pump it down and do that sort of stuff. They're pretty nice. So. Yeah.
What would be your educated guess how hard it will get to hack the board? Like Xbox 360?
Well, so the Xbox 360 is an interesting divergence from the classic security model. Like a lot of people relied upon circuit board techniques like epoxy and potting and stuff like that to obfuscate things, and those are really, really ineffective. They're not very good. The 360 is probably the first the large-scale commercial deployment I've seen of very heavily silicon-based security. That system's probably, you know, I mean, there's a known flaw in it that ends up being a DVD drive, which is, you know, kind of, they built the great castle without the back door open. But if you actually want to attack the core silicon security itself, it's reasonably tough. But you know, I think there's good techniques for getting into it. They just haven't been developed as much because there's not as much demand. But you know, with time, the techniques come, and you know, we'll find a way to circulate through these things. It's actually a very big concern because IBM is now trying to sell that sort of technology as an IP core to ASIC manufacturers. Say, if you want to build secure buses, use this technology, add it to your ASIC, and it encrypts all your buses, right? And that's just a nightmare, because now you can have completely clear buses and you tap them all you want, but you know, you can't actually attack the system because they burn the keys in at manufacturing time in a secure facility, and they force you to do the silicon. So I think it is pretty important moving forward in the future to try and find ways to get around that, because you know, once manufacturers start locking you into what software you can run, then whoa, all of a sudden your PC can't run Linux anymore because sorry, it's, you know, it's only so.
Impossible? Is it going to be possible?
No, it won't be impossible. Nothing's impossible.
Not cost effective, probably?
I think there might be cost-effective techniques coming up, because typically, I mean, it's all about finding the right way to rub it, right? So, you know, there's that story of a guy who walks into the big machine and he, you know, taps on the machine and starts working, and he charges him like $25,000. He says, you know, the tap was 25 cents or $24,000, and it's knowing where to tap. So a lot of these hardware security systems, you just need to tap them the right way, and bits will fall out of them, right? Because they leak all over the place. It comes through the power supply, they come through the outside buses, out-of-band things, backdoor ports, JTAG ports, all these kinds of things. Because the manufacturer themselves can't, if they build a completely purely secure system, if they have any defect, that defect's a loss to the line. And they're running at like 99% yield, and they rely on being able to rework 10% of them to get there. All of a sudden they lose 10% of their margin if they use security. There's no way they're going to give that up, right? So those things are always left behind, and usually you can sort of jiggle them a bit and get what you need out of it enough to move things forward. We'll see. I mean, I could be wrong.
Sure.
Yep.
Have you encountered like hardware-based cryptography that's built in, trusted computing systems where you have to figure out keys from everything is encrypted from each component to each component?
Yeah, I mean, I've encountered some of those before. Yeah.
Like across the board, or just
Usually it's component to component, but like 360 is actually across the board generally. I mean, everything's encrypted: CPUs, GPU. Some people say the south bridges. A lot of encryption there. So they're very paranoid.
Have you ever encountered anti-tamper products?
Any what?
Anti-tamper.
No, I actually haven't encountered many anti-tamper measures like the FIPS government standard and so forth. I know that they have like these membranes where you penetrate them and it zeroes out all the memory. I haven't been given like a government level security module. Typically in commercial hardware, anti-tamper measures are very much looked down upon because field service or customer just opening up and stuff, they don't want to have to do the warranty return, or if there's a puncture just in shipping, it's not worth the risk to the manufacturer, to lose all profit altogether, right, by putting anti-tamper measures in. So, it would be great, like if something like an Xbox where they would put like this membrane, so if you open it up, everything's zeros, right? But, there's too many things that can go on, they would just, not cost effective for them, so. I haven't seen that yet, not on the
Have you ever worked with smart cards?
I've worked a little bit with smart cards, a little bit.
You're trying to reverse that?
I mean, there's one great thing about smart cards is a lot of papers on it out there. So I've done a little work with them trying to reverse them, but really, if you want to learn more about them, there's a whole bunch of like cryptography research in San Francisco, I think, has a big volume of papers written about how to invade smart cards but even have to open them up, looking at the radiated signatures and so forth. The smart cards themselves have gotten very sophisticated. They start putting like layers of metal on the top, so if you open them up, you can't read them. They have what we call alarms on the chip, so if you reduce the VDD or you glitch the clock, it actually sets an alarm and the chip shuts itself down. So they're very paranoid when they build these because those are meant to be tamper-resistant modules, like chips, right? But they haven't really seen tamper-resistant at the board level yet. So, the smart card modules are pretty well engineered. If you get the right one, I mean, you have to know what they're doing inside. They're pretty good. So, any other questions? It's dinner time, so. All right, thanks, guys.